We're starting off with just a basic x squared curve, but we're really focused on what's happening at x equals 3. We're going to look at the limit in 3 different ways. The first way we're going to look at it is a right-sided limit. So limit as x approaches 3, when it looks like an exponent on the number as either a positive or negative, it either means coming from the right or coming from the left. Positive means coming from the right side and tracing down towards that x value, what y value are you headed towards. Negative means tracing from the left side and headed towards that x value, what y value are you headed towards. If the positive and negative agree, then and only then does this limit exist. It exists at whatever number I'm approaching from both the left and the right. If I'm approaching 2 different values from the left and the right, then the limit does not exist or it's undefined. For f of x to be continuous at x equals 3, the limit needs to exist, it needs to be the same from both sides, and f of that value needs to be equal to whatever the limit is. So I can't just have a hole in the graph taking me away at that one specific point, which is similar to stuff that we did in 1.3 where we found those indeterminate cases 0 over 0. In this case, it's a basic x squared graph where it is continuous everywhere. If I were to trace it, I would never pick up my pen. It's a continuous graph, which means as I approach 3 from the right side, I come down and come towards this x value of 3. It's headed towards this y value of 9. The same thing happens as I approach from the left side. I'm headed towards this x value of 3, tracing along this curve from the left, heads towards a y value of 9. If the right-sided and left-sided limits agree, then that same limit is the overall limit. When I'm asked if it's continuous at x equals 3, well, yes, it approaches the same place, approaches a y value of 9 as x approaches 3, and the curve actually does have a hard point right there that tells me when I put in the x value 3, I get back the y value 9. So yes, it is continuous at that point x equals 3. Here we have g of x, which is just a basic absolute value graph. So it bounces here at 0, but it still is something that is continuous the whole way. I never have to pick up my pen. If I look specifically where we're looking in these limits, at 1, from the right side, an x value of 1, if I trace along the curve, goes towards a y value of 1. From the left side, if I trace towards it, an x value of 1 goes towards a y value of 1. That means the overall limit does exist, and it is 1. Is g of x continuous at 1? Yes, it is. This is the value at 1. So again, the answer is yes here. When asked to discuss the continuity of these 3 possible graphs in question number 3, the first one has a jump discontinuity. On the worksheet, you can see specifically where it's happening, but basically, just graphically, what's occurring here is I have a line where everything's normal except at this one point. The limit would approach the same thing from both sides, but at this exact point, the curve is actually here. So f of this value, I think it was 3, is actually up here at 7 instead of at like 3 where we expect it to be. In this case, it's not continuous because I have this jump discontinuity where I'd go here, have to pick up my pen to hit this dot, then come back and keep going. So the limit would exist there, but it would not be continuous. Second graph, part B, I can trace the whole way. Nothing here happens that makes it discontinuous. So this is a continuous function. For part C, this has an asymptote. This is a discontinuity. Here I go all the way down to negative infinity and start back up at positive infinity as I come back on. That's going to be a case where I'm dividing by something that would be dividing by 0 at that point, and it flips from positive to negative as I cross that threshold. So this is discontinuous at that asymptote. When we talk about the intermediate value theorem, what the intermediate value theorem holds is that if a certain interval, certain function, it's continuous over that interval, the function is, then whatever the lowest value and the highest value of the function is over that continuous portion, it has to hit every value in between. And you can specifically solve for any individual value. Reason for this, let's say the intermediate value theorem said that right here we had a value of y equals -2. And right here we had a value of y equals 7. If I never picked up my pen going from a y value of -2 to a y value of 7, somewhere in here, at least once, I had to hit every possible value between -2 and 7. So somewhere, I'm not sure where, but somewhere this curve hits 5. Let's say it's around here. Somewhere this curve hits 1. Could be here, could also be here. At least once it happens, because on a continuous function, I have to touch everything as I go through. So what we're going to do to set up that it applies is we're first going to plug in 0 and 5, see what they give us, and then see that the f of c that we're looking for is in between those two values. We're also going to have to comment on, is this continuous over this interval? So x squared plus 3x plus 7 is continuous over this entire interval. It's continuous over the entire function. When I go to plug in a 0, f of 0 gives me 0 squared plus 3 times 0 plus 7, which just gives me 7. F of 5 gives me 5 squared plus 3 times 5 plus 7. That gives me 25 plus 15 plus 7, which gives me 47. That tells me by the intermediate value theorem that anything between 7 and 47 must be somewhere on this function between the x values of 0 and 5. Since we're looking for 17 and that does fall between 7 and 47, we can find where this function equals 17. To do it, we're going to plug in 17 for the value here of f of x, solve back for the x. That'll tell us what this c that's guaranteed by the theorem is. So I'm going to plug in 17 equals x squared plus 3x plus 7. I'm going to subtract 17, subtract 17. That gets me to 0 equals x squared plus 3x minus 10. I could use the quadratic formula to solve this. I'd rather recognize that this is a trinomial that can be factored. Specifically, it can be factored into x plus 5, x minus 2. -2 times 5 gives me -10. 5x minus 2x gives me positive 3x. So these are my factors. The question is, what makes this 0? One thing that makes it 0 is -5, but that's outside of my interval. So that's not what was guaranteed by the IVT. As opposed to this factor, x minus 2, to make that 0, we need a positive 2. Positive 2 does fall between 0 and 5, which tells me that c must equal positive 2. If I do the same steps for part B here, I start by saying, is it continuous over the interval? Well, here we do have something to worry about, specifically on bottom here, this x plus 2. A -2 would be something that made this not continuous, because if I put in a -2, I get a 0 on bottom outside the domain. -2 is not in between 0 and 5, so it's not going to cause a problem over our interval. So even though this would end up being something that looks like our asymptote here, where the asymptote's actually occurring isn't in the region that we're looking for. So we can move forward with the IVT. Intermediate value theorem only is applicable over the region we're looking for if it's continuous over the region that we're looking for. That holds, so we can go ahead and say, what's my low value, what's my high value, is this between the two? If I plug in a 0, I get f of 0 equals 0 minus 5 over 0 plus 2, which gives me -5 over positive 2, or -2.5. If I do f of 5, that gives me 5 minus 5 over 5 plus 2, which gives me 0 over 7, or 0. -1 is in between -2.5 and 0. So we know that the intermediate value theorem tells us if it's continuous, which it is over that interval, we can find a -1 as the y value. To do it, we're going to put in -1 equals x minus 5 over x plus 2. When we go to multiply both sides by x minus 2, we do have the caveat that x cannot equal negative 2, but that wouldn't have been in our interval anyway, so we don't really have to worry about it. X plus 2 gets multiplied by negative 1, and it becomes negative 1x plus 2 equals x minus 5. Negative 1 times x gives me negative x. Negative 1 times 2 gives me negative 2, still equal to x minus 5. I'm going to add 5 here, add x here, which means I add 5 here, add x here. These go away. Negative 2 plus 5 gives me 3. These go away. X plus x gives me 2x. That means my final answer would be x equals 3 halves, or 1.5. 1.5 does fall within my interval. If I put 1.5 in, 1.5 minus 5 is negative 3.5. 1.5 plus 2 is positive 3.5. Negative 3.5 divided by positive 3.5 does give me this value of negative 1. So my C value here is C equals 1.5. When we consider the following functions, and we're trying to say what happens as I go from the left and from the right, does it approach negative infinity or positive infinity? The best thing to do, going from the left, do something slightly smaller than the x value. Going from the right, do something slightly larger than the x value. See whether that gives you something that is, you know what? I need to stop this. I'm sorry. Should it be negative 2 here? All of these should be negative 2. That's my bad. All right. I am changing this to x approaches negative 2. All these should be negative 2. I'm just realizing I need the one that makes it so that I get a 0 if I put it in. Apologies. I just misread that as I was writing it up on the board. So when I put in a negative 2 here, I get 1 over 0, which means things are no good. I want to see what happens when I put in something further left than negative 2. So for instance, if I put in negative 2.1 here, 1 over negative 2.1 plus 2 would give me 1 over negative 0.1, which would give me negative 10. If I instead did negative 2.01, it would give me negative 100. Negative 2.001, it would give me negative 1,000, and so on. You would see that these get bigger and bigger the closer I get to negative 2 from the left, but always they get more and more negative. For that reason, this approaches negative infinity from the left-hand side. As opposed to if I do something just slightly larger than negative 2, so on the number line slightly larger than negative 2 would be like negative 1.9. Negative 1.9 plus 2 would give me positive 0.1. 1 over 0.1 would give me 10. If I tried instead negative 1.99, that would give me positive 100. Negative 1.999 would give me positive 1,000. Hopefully you can see that I just keep getting larger and larger numbers towards positive infinity when I approach from the right-hand side, with numbers slightly larger than negative 2. When I put it in here, no matter which side I'm approaching from, whether it's the left side or the right side, when I'm approaching this negative 2 value, inside of the square root, I'm going to get something really small that when squared becomes even smaller, but when squared always becomes positive. For that reason, when I divide 1 by something positive, it doesn't matter whether I've come from the left side or from the right side. Each time I'm going to get a positive answer. Because here, if I do negative 2.1 plus 2, that would give me negative 0.1, but squared is positive 0.01 or positive 100 for a final answer. Same idea if I did negative 1.9, I'd get 0.1. Squared is 0.01 or positive 100 for an answer. As I got closer from either side, it would make the y value bigger, but always positive. For that reason, I would get positive infinity here and positive infinity here. As opposed to this situation in C, which is the exact opposite. Here, the squaring makes the bottom positive every time, but since the top is negative, it's always going to be a negative divided by a positive. A negative divided by a positive is a negative. So each of these will head towards negative infinity. If I wanted to test it by doing a left-sided value, Left side is something slightly further left on the number line, so this would be like negative 2.1. Negative 2.1 plus 2 would give me negative 0.1. When squared, that would give me positive 0.01. Negative 1 divided by positive 0.01 would give me negative 100. That's why this gets closer to negative infinity the further I go on. When I'm asked to find these vertical asymptotes, a vertical asymptote occurs when I can make the bottom 0 in a way that wouldn't cancel with something on top. Here, the way to make the bottom 0 is by putting in 0 for x. So here I have a vertical asymptote at x equals 0. For this equation, I'd want to check and make sure that I can't factor top and bottom in a way that something would go away. The bottom would factor to x plus 2, x minus 2, but neither of those is a factor of the top. Really, all I can do for the top is take out an x to make it x squared plus 15. Since nothing cancels, I look at what could make the bottom 0. Anything that could make the bottom 0 becomes a vertical asymptote. Here, negative 2 makes this 0. Here, positive 2 makes this 0. That means I have two vertical asymptotes. The first one is at x equals negative 2. The second is at x equals positive 2. When I'm asked to determine vertical asymptotes and discontinuities, the vertical asymptotes are the ones that make the bottom 0 and do not reduce with anything above. The discontinuities are the ones that make the bottom 0 but do reduce with something above. So here, if I were to factor the top, it would become x plus 1, x minus 1, which does reduce with the bottom x minus 1. When two things go away like that, they don't give me the vertical asymptote the way this x equals 0 and this x equals negative 2 and 2 did above. Instead, they give me a discontinuity. Specifically, they give me a discontinuity at x equals positive 1, because positive 1 would make each of these 0. When I go to the second answer here on part B, I have x squared plus 10x on top. I can factor that by taking out an x and leave myself with x plus 10. On bottom, x squared minus 4x, I can factor out an x and leave myself with x minus 4. The factor which is present on both top and bottom is this x, which means I have a discontinuity at x equals 0. I have this other factor, x minus 4, that doesn't have anything to cancel with on top. That's going to leave an asymptote. So where the asymptote is occurring is where this can equal 0, which is at the x value of 4. So I have a vertical asymptote at x equals 4. It's possible to have multiple discontinuities and multiple vertical asymptotes in the same problem. I basically want to make sure that I'm fully factoring both top and bottom, seeing anything that cancels, seeing anything that makes the bottom 0.